Okay, thank you. Thank you very much. Okay, guys, now you see my screen. I really glad to see all of you on today's session. And let me make several small announcements. First of all, tomorrow was a deadline for the first homework. I'm really appreciated for those who submitted it. Yes, good job, guys. And also I sent the feedback about the first homework for everybody who submitted it. If some of you submitted homework and didn't receive feedback, please write me in Slack or email directly, and we will fix it. After all, yeah, good job, everybody who did it, and almost everyone get a good grades for this homework. Second announcement, today I will publish second homework, and the second homework will be dedicated to mastering pandas and data processing, tabular data processing. Now I will demonstrate you second homework. I have it in my folder here. Let me show you. Okay, second homework about pandas practice. And in this homework, I expect you to work with a dataset which you can obtain from this link. But also, I will share this file with you. This is houseprices.csv. Sorry, typo here. Should be house prices. And the second homework, let me show you. You see, yes, this is an outline for second homework. On the left part of the screen, you will have these questions, question 1, question, and so on. And you have six sections in this homework. You will work with data inspection, data exploration, data selection, different logical condition and logical masks, creating new columns. And then after you complete all these tasks, right now you see the solution. I already have a solution, but for you, when you will receive this homework, I will just delete these cells. You won't see the solution. You will just see the output, expected output for this particular cell. So you will see what I'm expecting from you in this task. And after all, you can like patch your code and make it like working like this. So you will see output of every single cell in this Jupyter notebook, but you won't have a code. Solution is in my folder. You will have it without solution. And when you, sorry if I typo here, and when you solve all the problems, maybe you will skip some problems if you see that they are too complicated. You need to restart your Jupyter notebook. You see this button, clear all outputs and run all. You should do like this to make sure that your Jupyter notebook is linearly executable. So there is no errors and no situation when cell which is lie below expecting some variables from the cell which is even lower. So this is not a correct situation. Your notebook should be linearly executable from the top to bottom. And then you need to save your solution. And once again, you should publish it on GitHub, like a situation with the first homework. After you publish your homework on GitHub, you should send me a link to your GitHub using email in the same manner like you do in the first homework. So the output, the final outcome of the second homework is a Jupyter notebook with a solution of all the problems. You see, it's almost, I would say, 25 problems here. And after you complete it, I really hope that you will master all the simple pandas operations. Okay, that's all. I will publish it today on a GitHub of our Guide Tribe cohort, number 3, and I will share a link on a Slack. So please give a try to this homework, and I will be really glad if you submit some solution. Guys, one more thing, even if your solution is not perfect, you don't know how to solve some problems, please submit it. Even if you solve like 50% of problems, it's already not so bad. Like better to submit something than not submit the the not submit. So yes, that's all about second homework. Let me save. Yeah, let me save it. You will find it in our GitHub today. Now let's move to the practical part of our lecture. Let me create new project, new folder, and today is practice number 3. Practice 3. As always, we will work using Visual Studio Code, and now I moving directly to it. Desktop, guide tribe, practice. Yeah, practice 3. Okay. As I announced you previously, today's lecture will be dedicated to the statistical concepts, to the essential statistical concepts. Please, don't worry really a lot. We don't go deep into the mathematics, into the some formulas, calculations. We will just briefly introduce important statistical concepts. We will check how you can use this concept using Python programming language, and how actually you can report important statistics about your data to other workers, managers, and so on. So let me create new Jupyter notebook as always, and this Jupyter will be called statistical concepts. Statistical concepts. Okay. As always, when we are working in a data science project, our very first steps when we are doing some exploration, we need to import some libraries. So as always, we will need pandas, and we imported this PD. Also today we will need a new package, relatively new. We will need numpy as NP. NumPy is abbreviation for numerical Python, and this library used for creating random numbers, distributions, and linear algebra. So if you need to work with vectors, if you need to work with matrices, you definitely should work with NumPy, because it is fast. It is much faster than using a regular Python lists. And in NumPy, all this operation is perfectly optimized. So if you need matrix multiplication, matrix summation, vector manipulation, you should use NumPy. And also we will need some visualization package. For these purposes, we will use matplotlib as always. Matplotlib.pyplot SPLT, and also we will need Seaborn as SNS. These two packages is for data visualization. Okay, let me think. Yeah, I would say that this is okay for today. Also, as always, we need to select a kernel for our project. I will use Python 3.11. In several seconds, it will start. Okay, so what is the plan? Today, I will demonstrate you how you can calculate different statistics using simple data. First of all, let me introduce you numpy. NumPy is a library, as I already told, that allows us to generate random numbers. So let's actually dive and try to generate some random numbers using it. For these purposes, I will call method.random, np.random. np.random, and inside this random module, you can generate random numbers from different distribution. You can generate numbers from normal distribution, from uniformal distribution, from Gaussian is the same as a normal, from log normal distribution, and whatever you can imagine. So let me generate number, just a single random number, .rand. I execute the cell, and you see I generated random number. Let me execute it one more time. You see another number. And each time I will execute the cell, I will get a different number. What else is important about NumPy? That in NumPy, you can set a size of a vector of random numbers. What does it mean? It's actually really simple. You call parameter called size, and you say a number, size equal 10, for instance. Let me generate. Oh, sorry. No, it's not like this. Random. random size equal 10. And now already you generate 10 random numbers. So instead of doing like this for e in range 10 and calling this function, which allows you to generate single random number, you will just use another method which allows you to do the same manner just in one string without writing this for loop. So please keep it in mind because we will use it really frequently today. np.random, and as you expect, if I change the size parameter, it will be the vector of size 100. I mean, you can like try and calculate that this size is 100. What else is important about this .random? Let me dive into the documentation of this method. For these purposes, as always, we call this question mark. Let me see. As you see, return random floats in the half open interval. So what is important? That random numbers generated by this method is from 0 to 1 explicitly. And what else we can do with this random model? We can generate uniform. Uniform is a random number from another distribution. And now to understand what actually the difference between this np.random and np.random uniform, let me write a size equal 100. We need to introduce a concept of distributions. So what is the distribution? Let me plot you, and I would say that this picture will explain you everything. To plot a distribution in Python, we will call this seaboard. Let me call this section plotting distributions. Yeah, this section will be about plotting distribution. To plot a distribution, we need seaboard, and here you can see method histplot. And this method histplot expects from us some vector. So for instance, I can copy this line, I can paste it here, and this histplot will plot us a histogram using 100 random numbers. Also, we can add some like support methods as always, plt.show, plt.grid with parameter alpha equal 0.4. I just like it. And plt.title, for instance, plt.title. And this will be titled as uniform distribution. Yeah. Okay, let me execute the cell and let's see the result. You see, this is a uniform distribution. Right now, we have only 100 numbers. So actually, this distribution is not like a perfect uniform because we have not really a lot of numbers. Let me copy the same code, and instead of using 100, I will use 1000. Let me do it. You see, now it's become more clear how this distribution look in theoretical like expectations. Let me do it as this exercise one more time. I will use 10,000 random numbers. And you see, this is a uniform distribution. Right now, it's almost perfect. If I change this parameter to 100,000, I would expect that it will become more and more clear. So you see, each bar in this distribution expected to be in the same size with all other bars. So we expect that we have numbers, the same amount of numbers in each interval. So in interval from 0 to 0.2, we expect to have approximately 2000 numbers and the same amount of numbers in an interval from 0.4 to 0.6 and so on. I hope you got the idea. And you see one more important concept, that increasing the size of generated uniform distribution, like how many numbers we have in this distribution, we make it more clear from the perspective of human eye that how this distribution is really looks like. So let me do one more important, like it's not theoretical but practical exercise. How I can plot several plots in the same picture. Right now, you see it looks a bit weird because we need to scroll to actually check the results. We need to check this one, and it's actually take a time. So for this purpose, I will show you how you can plot several plots simultaneously on the same picture. Let me demonstrate you. I would say that this code, I cannot explain how it's worked correctly. You just need to remember how it's constructed. For this method, for this purpose, to plot several plots, we need PLT subplots. And this subplots method take 2 parameters. You can either specify number of columns or number of rows, or number of columns and number of rows simultaneously. Let's say that for this exercise, I will need a plot which will have 3 pictures. Okay, 3 pictures. Number of columns equal to 3. And then I will use the same piece of code as here, SNS hist plot. And instead of using 1 parameter here, I will specify 1 more. Axis equal axis 1, axis equal axis 2, and axis equal axis 3. This axis 1, axis 2, axis 3 is a like coordinates of our 3 pictures, which I expected to see right now. plt.show. Let me see what's the result. You see right now we have 3 pictures, 1, 2, 3. Okay. Now it looks a bit ugly. So how we can make these plots of several pictures look better, look prettier? First of all, we can use share y parameter. You see, right now we have y-axis, and this y-axis is a bit intercept with plots. And for these purposes, I will remove it from plot number 2 and plot number 3, and we will have it only on the first plot, because the dimensions in this y-axis is the same for all 3 plots. What else we can do? We can pass one more parameter, fig size. Yeah, this is just a size of a figure in some units. Frankly speaking, I'm not sure what this unit is, but we will do an experiment. For instance, I will show that size of the figure should be 12 units on x-axis and 6 units on y-axis. What else we can do? We can increase DPI, number of pixels per 1 square centimeter. Let's use it 150. Okay, let's try to see this picture. Now it looks a bit better, but I would say that this parameter should be equal to 4 to make it, now it's better. Okay, why we actually do it? Because we want to see 3 pictures simultaneously, and we want to see it with different parameter of size. Remember, like we did last time, we checked size equal to 100, size equal to 1000, size equal to 10,000, 100,000. Now let's see how it looks like on this picture. Let's do like this: 100, 1000, 10,000. Okay, let's execute. Yes, you see right now, you see how this distribution changed, how it's visually changed with increasing number of observations in each of them. Okay, that's fine. And what else we can do? Let me demonstrate how I can change this code. So instead of 3 pictures in a row, I will have 3 pictures in a column, for instance. For this purpose, I just change first parameter and rows equal to 3. Fig size, let me change it to a different manner. And share y parameter, I will remove it. Let's see. Oh, sorry, some error. Okay, and rows. Yeah, I made the typo here. Okay, you see, okay, this was a uniform distribution. Let me write a title. This was a uniform distribution. When you can see uniform distribution in real life, distribution. Imagine you dropping a dice. When you drop a dice, the expected result of dropping a dice is its uniform distribution. You will have the same probability of getting 1, of getting 2, 3, 4, 6, and 5. So it will be a uniform distribution if you will repeat this experiment many, many times. If you drop a dice 10,000 times, and plot a distribution of points, how many points you actually get, it will be a uniform distribution. This is an example of how you can see it in real life. Let me introduce you another distribution. This one is one of the most popular, normal distribution. And how you can actually do it using numpy. So for this purpose, np random and dot random. Yeah, this is just all. And this command will allow you to produce a normal distribution. Size equal to 100. Okay, let's do it. You see, we generated 100 numbers from normal distribution. And now let's copy paste this piece of code and demonstrate you how it looks like in reality, how normal distribution looks like in reality. What do I need to change? I need to change this uniform to a random. Yeah, you see, I just changed this parameter in my function. How to say? Actually, right now it's not a function. I just changing a rows. Now let's see how it looks like. Oh, something goes wrong. Something goes wrong with my. Yeah, I should use normal. Yeah, I fucked up. Normal. Is it okay? Yeah, right now you see, yeah, I messed up. Instead of np random.random, you should use np random.normal. Like we are like speaking in English, and if you are speaking in English, it should be normal. Right now, we generated 100 numbers from normal distribution, and on this plot, you see how actually normal distribution looks like in a case of 100 experiments, 1,000 experiments, and 10,000 experiments. You see, like it looks like a bell curve, and this is also an alternative name for normal distribution. You can see names like bell curve or Gauss distribution. Gauss distribution. What is actually important about this distribution? This is one of the most popular distribution in the world. I would say that even people who have no idea about statistics, who didn't ever do any mathematics, calculations, and whatever, they know about normal distribution. And why it is so? Because many natural processes can be like expressed using normal distribution. For example, you want to measure a height of a people, how high people actually is. Like one person is 175 centimeters, another is 160 centimeters, and so on. If you measure the height of people all over the world, you will obtain normal distribution. Another example, if you want to measure, for instance, salaries of a people, in most cases, you will measure salary of the people, you will normalize them to USD, for instance, and in majority of cases, it will be a normal distribution. And in nature, for instance, there is one example, a scientific publication, when person was measuring a length of turtles. He moved to an island and he started to measure a length of a turtles. He measured 1, 2, 3, and he measured like 10,000 different turtles. And when he plotted it, he used a histogram. He realized that actually length of turtles is a normal distribution. So this is a quite natural distribution. Okay, you definitely should know normal distribution, and you definitely should know how uniform distribution looks like, because this is a quite common question during your data science interview. Let me introduce you one more distribution. The student distribution. The student distribution. This one, T-student distribution, is an alternative, like a next step from the normal distribution. To generate a T-student distribution, you will call np.random, standard T. Yeah, standard T. And in T-student distribution, there is one parameter, df, and this df parameter is degrees of freedom. Let me show you. Let's actually play with this parameter and see how it looks like. df equal to 4, for instance. Yeah, let me see. Yeah, we generated number from a standard t-student distribution with degrees of freedom equal to 4. Now let's do the same exercise for our 3 plots, and instead of normal, we will use standard t. Sorry, standard t distribution size 10,000, and also right now it won't work because we need to specify number of degrees of freedom. Degrees of freedom, yeah, it will be the same for all plots. Let's see how it looks like. What is the difference? As I told you previously, t-student distribution is the next step from a normal distribution. And why it is so? Because right now you see that it is a bit sharper. It's a bit sharper than our normal distribution. And this degrees of freedom parameters allows us to measure actually the sharpness of a peak. You see this peak? This peak is actually sharp, but the shape of a distribution is almost like a bell, but it's not so. If we increase this df parameter, so instead of 4, for instance, we will use df equal to 10. df equal to 10. You will see that sharpness of a peak become a bit lower. And now our t-student distribution looks almost like a normal. And if you go further and start to increase this parameter even more, instead of 10, you will use, for instance, 30 degrees of freedom. Your t-student distribution becomes almost the same as normal. So you become closer and closer to normal distribution. But t-student distribution is not the same for the cases when degrees of freedom is pretty low. Yes, right now we checked 3 distribution. We know how to generate them using Python. And further, I will show you one more. Another distribution is gamma. Gamma distribution. Okay, in the same manner like we did before, we will call np.random and gamma. Right now, you need to specify several parameters to make it work. You need to specify shape and you need to specify scale. And as you see from the documentation, it allows us to produce samples from a gamma distribution. Let me demonstrate shape equal to, for instance, 2, scale equal to, yeah, let's make it by default, and size equal to 100. Yeah. Right now, we generated 100 samples from a gamma distribution. Now let's take our simple piece of code and change it with respect to this gamma distribution. And instead of degrees of freedom, right now we have this required parameter of shape. Sorry. Shape equal to 4. Yeah. Let's see. Yeah, you see right now, instead of having a normal distribution, we have a little bit curved it. So it's curved to the left side of the plot. You see how it looks like. Let me increase the number of samples in it. Maybe it will become clearer. Yeah, you see? And the form of gamma distribution is more about like uncertain events. For instance, you measure the time when your equipment should break. And this time can be modulated. You can actually express it using gamma distribution. So this is for events which is happening quite, how to say, not really often. Yeah, this is for modeling events which happening not really often. You see how the shape of this distribution changes with size. And now let's change the parameter of shape. For instance, let's use shape of 10, and shape of 10. You see this curveness of this gamma distribution from the left side become to change to a little bit to the right side. Okay, this is another useful distribution. sometimes during the interview, you will be asked about usage of gamma distribution, and you should say that this is for some uneven events which happen not really frequently. You should know what is t-student distribution, and sometimes you might be asked what is the this one parameter of standard t-student distribution and how actually the plots is changing when you change it. And you should say that sharpness of a peak become smaller and smaller, and when you increase degrees of freedom, your distribution become more like normal one. Okay, actually, I would say that exist more than 20 different types of distribution, but in practice, I would say in majority of cases, you will work with normal, uniformal, and t-student. These three distribution is must have. And in rare cases, you will work with gamma distribution, which looks like this. Okay, and we won't go deeper. We won't spend any time to demonstrate you parameters of other distribution. You can play it by yourself for the in your free time. Okay, now let's move to the actually descriptive statistics. Descriptive statistics. Okay. Oh, sorry, something is wrong. Yeah. What does it mean, descriptive statistics? Sometimes during the work, you need to describe your distribution. You need to say some information about it. You need to provide a listener, somebody asking you about how actually distributed salaries, how distributed, for instance, like waiting time of your taxi, how distributed your population. And you need to give some descriptive statistics. And actually, in a simple words, you need to describe your distribution in several numbers. You just need to give a numbers. The first type of descriptive statistics is a measure of how it is called. Let me check how it is called in English. Save message. Yeah, measure of central tendency. There is several measures of central tendency, and first of them is mean. It's just a simple mean. Let me take a piece of code to generating some distribution, and I will demonstrate you how to calculate a mean. Actually, to calculate a mean, let me have a piece of toy example. 1, 2, 3, 4. You just need to take a sum of a list, and then you should divide it by the length of the list. This is a simple mean. You can easily implement it in Python, but actually you don't need to do so because mean is already implemented. Let me generate some np.random.normal. Let's generate normal distribution with a size of 100. Let me create a variable. I will call it normal distribution. Now let's plot a histogram of this distribution. Hist plot normal dist plt.show. Yeah, we see how it looks like. And now let's actually calculate the mean value of this normal distribution. To do so, we just need to call method mean in numpy. You see the mean value of our distribution is minus 0.05. Let's actually plot it using our plt method. plt.axv line. And using this method, I can actually display a line which allows us to see a mean of value. But right now it's not actually visible because it's blue. Let's make its color equal red. And line style equal to dotted line. Okay, and let's have a title for our plot. Normal distribution mean. Yeah, right now our picture looks better, and you see how actually this mean looks like. Okay, another measure of a central tendency, which is really important sometimes, is median. What is actually median? imagine you have a list of numbers, the same manner, 1, 2, 3. And to calculate a median, you actually need to take a middle of your numbers. So you have 1, 2, 3. Right now it is sorted. You need to take a middle value. Right now, median of this list is 2. If you have a list of numbers which contains, for instance, 4, right now you need to sum up 2 and 3 and divide it by 2. So it's quite easy, understandable, and everybody make it at school. So median equal to 2.5, and here median equal to 2. You just need to take middle value, and if you don't know how to take a middle value, you need to calculate the sum of 2 and divide it. Okay, but as well, you can do it easily using numpy. np.median of list. Yeah, you see the result is 2.5. This was a toy example. Let me take our normal distribution and in the same manner calculate median. Oh, sorry, something wrong. Here, np.median. You see quite easy that our median is minus 0.2. Let me take this piece of code and demonstrate you how actually median looks like. np.median. Yeah, you see this red line is a median of our distribution. And here we have a mean. These two measures of central tendency. Another important measure of central tendency is mode. Imagine you have a list of numbers, 1, 2, 3, 4, and one more time 4. Mode is a number which is the most frequent in your samples. In this case, we have one occurrence of 1, one occurrence of 2, one occurrence of 3, but number 4 occurred 2 times. You see it 2 times. So in this case, mode equal to 4. And what is more important about mode, that it is not really useful when you're dealing with float numbers, with decimal numbers, because in this case, probability that some numbers will appear more than one time is extremely low. So mode is more about cases when you are working with natural numbers, with numbers like 1, 2, 3, and not when you're working with decimal numbers. So for the case of this normal distribution, which we were working for, most probably we won't be able to calculate mode. It will give an error. Yes, something is wrong here. Okay, these 3 measures of central tendency. You need to know how to calculate mean. You just need to take a sum of all your numbers and divide by how much numbers you have. And another is median. Median is actually a point which split your data set in 15%. So 15% of data is here and 50% of data is on the right. Let me just change median. This is median. 50%. This also another name for a median is a 15th percentile. So 50% of data here, 50% of data here. Just a point to split our data in 2 equal parts. Also, what is important, that mean and median in this case is not the same. Let me demonstrate you. If we display them on the same plot, color equal to yellow. Yeah, you see right now mean and median. We have mean with yellow color and median with the red color, and now them they are not equal. And actually, this is the same situation for almost all the distribution. And in real work, you need to choose which measure of central tendency is better for describe your data. Why it is so? Because there is one problem of mean. Mean is really sensitive to outliers. Imagine a case you need to calculate a mean salary. You have 100 people with salary of $2,000 per month. And then 100 first person is Bill Gates, whose salary is $100 million per month. And from the just definition of mean, you need to calculate sum, and you need to divide it by the length of your samples, by the number of samples. And in this case, your mean will be extremely like not representative. Why it is not representative? Because when you sum 10 people, 100 people with $2,000 and one person with $100 million, your mean will be approximately, I would say, $20 million. And this is absolutely not representative for your group of people because the mean salary is too high. And in this case, mean is not really good. Mean is not really good when you have outliers. And in this case, median is much, much better. Because if you calculate median, in the same case, the median will be still $2,000. And this $2,000 of salary is much better, allows you to describe your data, to describe a central tendency of your data. Okay, to sum up this part, you have a possibility to describe a central tendency of your data using three different approaches: mean, median, and mode. Mode, the last one, is not suitable when you are working with decimal numbers because it's just not working. You don't, the probability to have the same numbers is really low. Mean and median is quite okay in the majority of cases. Sometimes you need to use mean, sometimes you need to use median. Median is better when your data has outliers, and mean is better when you need computational power. I just want to mention that to calculate mean, you need less computational power. Right now, we are working with 2 examples of 3 samples. And to calculate mean, it's really simple. It's no problem. But sometimes you are working with samples of thousands, millions of data points. And in this case, calculation of median is much more complicated than mean. Just from the point of view of computer, computation to calculate mean is easier. This is about algorithmic complexity. So this is just, you need to pick your cup of tea, you need to make a choice. Okay, this was the first part, measure of central tendency, and another, let's move to the second part. The second part of statistical measures of variability of data. Let me generate some numbers. Oh, actually, yeah, np.random. No, I decided, yeah, let's use real data for this purpose. To read this, we will use our data set from the last time. PD read CSV. We will use data set. Let me see how it's called. Yeah. Last time I was working with a data set called yeah, salaries, ds.salaries. And right now we will demonstrate measures of variability on this data set. Practice number 2. Okay, and now we will work with a column called salary in USD. Yeah, I just thought that right now we just generating different distribution, different numbers, and maybe it will be much better to demonstrate you all the concept using real data. Let me do the same for the DF salary in USD. For the previous concept, hist plot DF salary and plt dot show. Oh, yeah, right now you see the histogram of real data, the histogram of salary in USD. Let me do the same exercise for this case. and we will check if the median and mean of this distribution like lie close to each other. Okay, let's see. Oh, you see, right now it's almost a perfect case because yellow and red line are almost in the same place. So this distribution can be described really well using both these two statistical concepts. You can describe it using mean and you can describe it using median in the same way because they are really close and you won't see any problems with it. Okay, that's great. Now let's move to the second part, measures of variability. Actually, when you're working with data, you may expect to be asked, what is the variability of your data? And measure of this variability called variance. To calculate variance of your data, let me take our salaries. You need method np.var. This is variance. Let me see. The variance of our data is 3. Okay, no matter. What is bad about variance? Why it is actually not a perfect measure? Because variability measured in squared units. Let me explain the concept. For instance, you plotted your salary in USD and salary measured in dollars. But when you use this np.var, you receive a value which is measured in dollars, dollars squared, dollars of the second power. And at this point, it is really not easy to interpret this measure of variability. Imagine a situation like your manager on a work asked you, what is the variability of our data? And you calculated this variance and you explained to him, oh, our variability is like $39 million squared. Actually, it won't give any useful information to business, to stakeholders, and so on. So at this point, in practice, almost in every case, we use standard deviation. This was variance, not really useful, I would say. This is variance. In real cases, we use another concept, is standard deviation. Standard deviation. Actually, standard deviation is just a square root of variance. To calculate standard deviation, you need method np.std. np.std, and we will calculate standard deviation of salaries in USD. np.std. You see that right now already measure units of measure for this standard deviation is not dollars squared, but just dollars. So if you report this value to some stakeholders, it will be already much more understandable at this point. And actually, we can try to check. Yeah, you see that right now, standard deviation is just a square root of our variance. And since we're taking square root from dollars squared, right now it's measured in dollars. What is the physical mean of this standard deviation? Let me demonstrate you. For this purpose, I will generate several distributions, and I will reuse this piece of code. Yeah. Right now, I will demonstrate you how different standard deviation can change the visual of a histogram. For this purpose, let's use normal distribution. And when we are creating values from normal distribution, we have two parameters. Let me demonstrate you documentation. We have location and scale. Location is a mean value. So you can specify what is the mean value of random numbers which you should generate, where they located actually. And the second parameter is scale. And scale is the same as a standard deviation here. Let me demonstrate you. I will generate several distribution with scale 1, scale equal to 3, and scale equal to 5, for instance. And the size of this distribution will be 10,000 for all of them. We right now not experimenting with size. Okay, Now let's see the effect of this distribution. Actually, right now we don't see. Yeah, we see. Let me do one more adjustment. Share x equal true. Yeah. Right now you see the effect of different standard deviations. We have standard deviation equal to 1, we have standard deviation equal to 3, a standard deviation equal to 5. And you see how different actually normal distributions looks like with different standard deviations. If our standard deviation is pretty low, our normal distribution is really look sharp. All the values extremely close to the mean. You see, it looks like this. If our standard deviation becomes larger, for instance, it's equal to 3, our normal distribution become wider. The points right now is far away from the mean value. Mean value of our distributions, of all our distributions, is 0. You see, 0, 0 in the middle. And if we increase the value of standard distribution, our points just become spread a little bit more from the mean value. From the physical point of view, this is an average distance of each point to the mean value of our distribution. We measure distance to one point, to another point, to third point. For all 10,000 points, we measure this distance, Euclidean distance. And then we just calculate average. We just make an average distance. And if we increase this average distance, also our normal distribution become wider and wider. We, for instance, can add one more example, scale equal to 10, and we will get extremely big distribution. X4, X4. Yeah, let's see. Yeah, it's become wider, wider, and wider. We are just changing the standard distribution. Let me also add x is unset title, just to make it absolutely clear. std equal to 1. Yeah, I have std equal to 1. I have std equal to 5 to 10, and let me change this 2, 3, and 4. Yeah, you see the picture, increasing standard deviation, our distribution become wider. Now, actually, let's move to another measure of variability. You need to understand that variance is a measure of variability, but variance is not really good. So at this point, we should take square root of variance, and square root of variance called standard deviation. Standard deviation already measured in the same units as our distribution. So if you measure salary, it's measured in dollars. If you measure height of people, it's measured in centimeters. If you measure area, it will be measured in square centimeters, for instance. And if we increase standard deviation of our distribution, the bigger standard deviation, the more it's spread around mean. Okay. Another measure of variability is just range. How to calculate range? I would say that this is quite intuitive concept. You just need to take minimum value of your distribution. In this case, df salaries, how it is called, how I forgot how it is called. Yes, salary in USD. You just take difference between minimum and maximum value of our distributions. Let me demonstrate you maximum value. You take maximum, you take minimum, and you find the difference. So you can conclude the difference between minimum and maximum value in your distribution is $444,000. Okay, it's not really kind of a complicated concept, but sometimes it is useful to use this as a measure of variability. Okay, another type of measure of variability is quantiles. Right now, quantiles, percentiles, and quartiles. Quantiles, is it correct? Quantiles. Yeah, I think it's correct. What is quantiles, percentiles, and quartiles? First of all, this is all synonyms. Sometimes you can see this name, or another name. This is all the same. First, quantile, which we need to know, is median. When we calculate np.median, median of our df.salary in USD, this is the same as we calculating 15th percentile. And as I told you already, this is median. Yeah. This is just a point which allows us to split our data in two equal parts. Imagine that we need to calculate not 15th percentile but 25th percentile. 25th percentile. From the physical point of view, 25th percentile allows us to split data in two parts. In one part, we will have 25% of samples, and in another part, we will have 75% of remaining ones. Let me demonstrate you how you can calculate different percentiles using NP. NP.one-tile. Yeah. Let me see which parameters it's actually take. Yeah, you see the example of this calculation. First of all, percentile. Yeah, let's start with percentile. NP.percentile. Percentile is just how we split our data in two parts. If, for instance, we will take our DF salaries and we will calculate 15th percentile, we obtain the same value if we calculate NP median, because it's the same. Percentile and 15th percentile and median is the same. If we calculate 25th percentile, we will obtain point which allows us to split data into 25 and 75%. Let's actually do some visualization to understand this concept. Hist plot df.salary. Okay, we have our histogram, and let's also visualize our 25th percentile. It will be clear. Ix v line. Yeah, you see this dotted line right here, 25% here, 75% here. Let's call it label equal 25th percentile. Let's also demonstrate 75th percentile, label 75, and change the color to red. And in the same manner, let's demonstrate median 5th percentile. PLT dot legend. Yeah, you see percentile, and you can display whatever you want. Percentiles, you can display first percentile, second, third, and so on. But the most popular one is 25th, 75, and 50. At this point, these percentiles have its own names. And these names is quartiles. Quarta, it means 4 in some language, maybe in Greek. So this is a point which allows us to split data in 4 parts, in 4 equal parts. So at this point, you need to know that 25th, 75th, and 50th percentile also has a synonym name of quartiles. And sometimes you might be asked to calculate quartiles of your data. And you need to know that this is the same as percentiles. And this is another measure of variability of your data. Calculating different percentiles of your data allows you to understand actually how many points lies in a certain interval. In a certain interval, for instance, you can measure where is 90% of your data is lying. For this point, you measure 5th percentile and you measure 95th percentile. And between these two percentiles, you may expect that remaining 90% of your data lying. Okay, this is another concept, quite important. And now let's actually check how we can use this concept in real task. For this point, I will introduce you another rule called the 3 sigma rule. 3 sigma rule. What does it actually mean? Sigma is another name for standard deviation. This is a first important tip, that sigma is the same as standard deviation. So 3 sigma rule, you can rephrase it as a rule of 3 standard deviations. What actually does it say? That if you calculate mean, and you add 3 standard deviation, you add 3 standard deviation, and on the right side and on the left side, you subtract 3 standard deviation. So between these 2 points, minus 3 standard deviation and plus 3 standard deviation, you will see 99.7% of your data if you have normal distribution. Let me demonstrate you how it looks like in real data. Once again, let me copy this piece of code, and instead of percentile, we will use standard deviation. Let me create some more variables. One of them will be upper bound, and this upper bound is equal to mean df dot salary in USD dot mean. It's equal to mean, and also for using this rule, we need to calculate standard deviation. STD. So upper bound of your data, we expected to have value of mean plus 3 multiplied by standard deviation. And another variable which I will need, lower bound, it is mean minus 3 standard deviation. Okay, now let's display upper bound, lower bound, and we don't need this value. Okay, you see right now we applied our 3 sigma rule on our data. Let me also display mean value. And let's use color equal red. Let's use red color for all our lines. Yeah, this is important concept in data science, that you expecting to have 99.7% of your samples inside these boundaries. We have our mean value in the middle, and we pointed out 3 standard deviation from our mean. This left boundary is mean minus 3 standard deviations, and the upper bound on the left is mean plus 3 standard deviation. And we expecting to have 99.7% of our data inside these boundaries. In the same manner, we can estimate a rule of 2 sigma. In 3 sigma, it's 99.7%. Rule of 2 sigma rule. If we calculate lower bound, let me call it lower bound 1 and upper bound 1. If we calculate mean plus 2 standard deviation and mean minus 2 standard deviation, let me also display it on our plot. Lower bound 1 and lower here 1, color equal to yellow. Something goes wrong. Yeah, I forgot to execute the cell. Okay, you see right now I displayed these yellow lines, and with respect to the rule of 2 sigma, we want our data should have 95% of samples inside these boundaries. This is 2 sigma. So here we will have 95% of data. And in the same manner, we can estimate 1 sigma rule. Let me create another 2 variables. if we subtract 1 sigma and add 1 sigma to the right, we will see 66.7% of our data. Let me do it. 2 color equal C. Yeah, we plotted another boundaries. This is 1 sigma, and in this area, we expected to see 66% of our samples. When it is really important to use this rule, sometimes you see your data and you see some really strange values. For instance, you see these boxes right here. They represent extremely high salaries. We are studying salaries, and some of the salaries is even higher than mean plus 3 standard deviation. In this case, you can call these values as outliers. Outliers is something which is actually not from this distribution, which is something strange. Sometimes outliers may be caused by the mistaken data. You just collected your data from a website and something goes wrong and you got some crazy value. Sometimes outliers is just the case with Bill Gates. Everybody got salary $2,000 and Bill Gates get really a lot of millions of dollars. This is another example of outliers. And using 3 sigma rules, you able to filter your data. So instead of working with kind of strange data, which has some extremely high or low values, outliers also can be in a minus position sometimes. You can remove them from data and process without them using this 3 sigma rule. So please keep it in mind. Sometimes it's really useful and sometimes you will use it in practice. Let me introduce you another concept connected with these measures of variability. It is called 1/2 EQR rule. How actually you can translate it? EQR, this EQR value, EQR is interquantile interval range, interquantile range. How to calculate EQR? To calculate EQR, you need to subtract 75th quantile minus 25th quantile. This is EQR. Why we are using this EQR rule? Remember, I told you that mean value and also the standard deviation sometimes not working correctly when our data has a lot of outliers. This is a kind of funny concept that you will use this 3 sigma rule to remove outliers from your data. But also sometimes this rule may be fooled by the outliers. If outliers extremely huge, your mean value will be also distorted by it in the same manner as standard deviation. But when you are working with quantiles, percentiles, and median, on a contrary, these measures is not affected by outliers. They are more stable, they are more robust. Let me demonstrate you on real data how actually you can see it. First of all, let's calculate interquantile range. EQR, as I told you, we need to calculate NP percentile 75th. Let's call Q75 from our data. Our data is DF salary. Yeah, I always forgot how it's called. We calculate 75th percentile, and also we calculate 25th percentile. Do like this. As I told you, we calculate interquantile range, Q75 minus Q25. And then we can introduce new concept of lower and upper boundary of our data. Lower boundary equal to Q 25th minus 1/2 multiplied by interquantile range. You see, it's a bit looks like previous concept of 3 sigma, but instead of mean on the first position, we use quantile. And instead of standard deviation, we are using interquantile range. And using this concept, we make our calculation more robust. And upper bound can be calculated like this. Let me plot this concept for you, how it looks like. Yeah, and plt dot title equal EQR rule. Yeah, you see, right now, results obtained by this interquantile rule is a bit different from the results obtained from the standard deviation rule. You see, upper boundary in this case on the right side of the screen showed us that some values which is higher than 300,000, some of these values is outliers. But right now, our criteria is more robust, and it allows us to actually find more outliers. You see, right now, upper boundary is more on the left side. It is actually lower than 300,000. So we have two different approaches, how we can inspect our data and how we check if this data has outliers. And this is actually a kind of an art of data science to understand where and when you should use this particular rule. Personally, for me, I prefer this interquantile rule. As I told you, this is much more robust. What is bad about interquantile rule that computationally, from the point of view of using CPU or GPU, it is more complicated to calculate. I won't go into the detail, but to calculate quantile, median, and whatever you want, you need to sort your data. And sorting is an expensive operation. But to calculate mean and standard deviation, you need just to do summation. And summation is a cheap operation. So you can do like this. Okay, these two concepts. Let's make, okay, we need to stop soon, right? Okay, let me introduce you one more concept. We don't make any pairs today, and we will finish in 40, yeah, I would say in 40 minutes. Another useful concept which you might be asked during your interview. This concept called the rule of big numbers. Big numbers. Or sometimes not rule, but law of big numbers. How you can like simulate law of big numbers in Python. Imagine you are dropping a coin. You just have a fair coin. You drop it, you check, is it tail or head? Is it tail or head? You drop it, and your task is measure what is the probability of head in tail in your drop, in your tests. Imagine you dropped your coin one time. You drop it one time, and you have a tail. Just from the viewpoint of probability theory, right now, probability of having tail is 100%. You have only one experiment, and in this experiment, you obtain tail. So you have 0 heads, you have 1 tail, and probability of getting head from your experiment is 100%. Imagine you drop it twice, second time. And second time, you see that it one more, again, it is tail. 2 times you got tail in your experiment. Once again, probability of getting tail is 100%. But you understand that it's not actually true. You expect that the probability of getting tail is 0.5, 50%. And I guess you understand that if you drop your coin many times, like 100 times, you will see that number of heads and tails become closer to 50%. You will have 50 tails and 50 heads. And now let's actually model this situation, and I will demonstrate you how you can formulate law of big numbers. How to do it in numpy. For this purpose, we will use np.random and randint with parameter 2. You see, when I call in this method once, it gives me 0. When I call it twice, it gives me 1. Again. If I use a for loop for this, for e in range 10, yeah, 100. if I do 100 drops, print, you see I have almost equal number of 0 and 1s, 0, 1, 0, 0. And you should imagine that this is a outcome of our experiment of dropping a coin. That 0, for instance, this is a tail, and 1, this is a head. 0 tail, 1 head, and whatever. What is a law of big numbers? Let me demonstrate how to do it. Imagine I will generate a series of experiments. p.random .rand int of 2, and size will be increasing. What does it mean? That we will start with size equal to 1. We will start with one experiment. We just drop a coin once. Then we will do 2 experiments. We will drop coin 2 times, then 3 times, 4 times, and the same manner till 100. Let me demonstrate you how it looks like. Yeah, you see, each of these arrays, each of this list is outcome of our experiment. And in each experiment, we increase a number of coins drops. So first experiment, just 1 drop, we have a tail, and the probability of getting tail is 100% because we have 1 experiment. Second, we have tail and head, 0 and 1, probability is 50%. Third probability, we have 2 tails, 1 head, and probability right now is 66.6%. In the same manner, we do many experiments until we have 100 drops. And in each experiment, we will calculate the probability. How to calculate the probability? We just take mean value. Mean value will return us a probability of getting a coin. Let me demonstrate you. Right now, you see, mean value of each series of experiments. Sometimes we have 0.8, 5.3, 2.8, and so on. And right now, we will see actually the power of this law. I will collect the result of 100 experiments into one array. And p.zeros and these zeros is 100. This experiments. Right now I created an empty array, an empty numpy array, and for each value in this numpy array, I will give a number which represent a probability of getting a head. Let's see. Yeah, let's check our experiments array. It looks like this. Yes, everything is fine. Let me also do this as a variable, and experiments. And experiments equal to 1000. And here it's also 1000. And now let's plot the result of our experiment. plt.plot. plt.show. plt.title. Law of big numbers. plt.xlabel. On x-axis, we will have n experiments. And on y-axis, we will have probability of tail. It actually doesn't matter. And let's plot plt.grid with parameter alpha equal to 2.3. Yeah, you see, this is a kind of a good demonstration of a law of big numbers. What actually this law tells us? That when we increasing the number of experiments, the outcome become the mean value, become closer and closer to theoretical expectation. In this particular case, when we are dropping a dice, our theoretical mathematical expectation 0.5. We will have equal probability of tails and heads. But when we do several experiments, for instance 10, this probability is not equal to 0.5. You see, it's 0.6, sometimes it's 0.4, sometimes it's even 0.2. And if we make many experiments, like you see, it's almost 1,000 experiments, these values start to oscillate around 0.5. You see this line, let me add it, plt dot ixv line equal to 0.5, and label равно expected value plt dot label plt legend. Something goes wrong. Because it's blue. Color equal red. IX H. Right now everything is correct. You see, the more experiments we do, the better our experiments. It's become closer and closer to expected value of 0.5. And when we do not a lot of experiments, like 200, this value is really not close to our expectation. Let me also improve this plot a little bit, and I will demonstrate you one more important concept. PLT, let's actually make it x1, x2, PLT dot subplots and rows and calls equal to 2. Okay, I just want to also add a histogram to demonstrate you this concept. Whatever, PLT ix SMS dot histplot experiments ix equal ix2. I made a small mistake here. And right now you also see a histogram of these values. And from this histogram, you also can see this picture is almost the same, but right now this is a histogram. You see that numbers of different experiments in which you have probability like 0.7. You have some experiments with probability 0.7, 0.6, 0.25, which is quite unexpected. But increasing and making it bigger and bigger number of your experiments, you become closer and closer to expected value of 0.5. This is a central limiting theorem. And I would say that this is a really frequent concept which will be asked during your interviews. So please understand it. And also, I would suggest you can do an exercise. You can try the same process, but not with a coin, but with a dice. Like you are dropping a dice. You have 1, 2, 3, 4, 5, 6. You have 6 different outcomes. But the expected value when you're dropping a dice is 3.5. So you can definitely try it out. And after all, you will see that central limiting theorem, or that this concept of big numbers is working in all cases. Okay, another important concept, which quite often will be asked during the statistical part of interview, is central limiting theorem. Limiting theorem. Okay. To demonstrate you central limiting theorem, let me first of all generate some distribution. Let's use gamma distribution. In P random dot gamma. We will use shape equal to 3, scale equal to 4, and the size, let's generate 100,000 samples of gamma distribution. Let's display it, hist plot of gamma distribution, plt.show and plt.title. This will be gamma distribution. Yeah, it looks like this. Imagine that right now we generated 100,000 samples. Imagine that we will take a subsample of our general population. Imagine that this is a general population of 100,000 samples. It will be whatever you want. For instance, it will be length of turtles from 0 to 30 centimeters. Okay, imagine you measure it and you take a subsample. Instead of 100,000, you will take np.random.sample. You will take subsample of gamma distribution of a size 100. Size equal, no, not 100, 1000, for instance. np dot sorry, something is wrong. Okay, I just should check my notes. You take np dot yeah, you take 1000 from gamma distribution. You take 1000 subsample. Yeah, it's just a number. I will call it subsample. And you measure a mean of this subsample. Let me create another variable. np.mean of subsample. And then you display a histogram, hist plot of your subsample of 1000 values. And also let's plot a title. And in this title, we will display mean value of our subsample. Mean value of our subsample. At this point, we will use f strings. Mean value, mean equal plt dot show. Yeah, we have 100,000 in our general population, 100,000 of turtles, for instance. Then we pick up from this 100,000 just 1,000, and we measured a mean. If we repeat this experiment of taking a subsample and measuring the mean, let me show you how it looks like. I just do it one more time. We will see a different mean of 12. Let me do it one more time. 12. Yeah, 11.85. You will see that if I will just copy paste this code, I will receive different result. I will receive different 1,000 samples. What does this central limiting theorem say? That if we repeat this experiment of taking a subsample from our general population, this is our general population. If we repeat this experiment many times, the mean values of our subsample will form a normal distribution, no matter what type of distribution we have at the first place. How we can actually simulate this situation and demonstrate this? Let me do a for loop. For loop will actually show us how many experiments we will do. For e in range of 1,000, I will do this experiment 1,000 times. So this plot, I will plot it 1,000 times. And each time I do it, I will measure a mean. And this mean I will store in some variable. Let me call it experiments means. np.zeros and experiments. Number of experiments, let's make it 1,000. and I will measure a mean of each subsample equal to mean subsample. And then let me run the simulation, experiment means. I will see how it looks like. And now if we plot a histogram, histplot, plt.show. Let's make a little bit more subsamples. Yeah. You see, right now we made 10,000 experiments when we picked up a subsample from our gamma distribution. We created gamma distribution. We picked up subsample. We measure a mean 11.8, 11.6, and we do it 10,000 times. And this means already distributed normally. So no matter which distribution was at the first place it was gamma distribution. After all, we will see this Gaussian or normal distribution. This is a central limiting theorem. Let me actually demonstrate you. This is a perfect normal distribution. Let's do the same experiment, but instead of gamma distribution, we will use, for instance, uniform distribution. Let's plot it. You see, this is a typical form of uniform distribution. Don't mind about title. I changed a shape of initial distribution. I try to make a subsample. You see, this is a subsample of our uniform distribution. I made another subsample. I calculated mean. Here I have a mean of 0.5. Here I have a mean of 0.49. And then I do the same operation 10,000 times. I pick a subsample, measure a mean, and plot the final distribution. And again, you see means are distributed normally, no matter that initial distribution was uniform. So let's actually experiment with different types of distribution. And you need to understand this concept. The basic idea that no matter which distribution was in the beginning, after subsampling and measuring a mean, we will end up with a normal distribution. This is an essence of central limiting theorem. Okay, Command G, sorry. Okay, guys, I suggest we will finish in 10 more minutes. I just a little bit adjust this code to make it working with other types of distribution. Imagine we will have this piece of code, this experiment. And also we need, this one, this piece. I want just to create a more kind of better code to demonstrate you that this concept will work with all other types of distribution. Subsample. Yeah, we will also need a subsample. Okay, will it work? Yes, subsample and final distribution. Yeah, let me create a function. And this function will be called central limiting theorem. Central limiting theorem. Instead of this gamma distribution, I will use just distribution. Yeah, distribution. And also we will pass as a function. And we will pass params. Okay, I would say that, oh, we have a question, sorry, I messed up. Okay, sorry guys. I will share this notebook to you. I need to finish because we have another meeting in 15 minutes. Let me sum up. Today, we discussed several important concepts. We discussed how to actually create different distribution using numpy. I demonstrated you what is the uniform distribution, how it looks like when you increase the number of samples, how you can create a normal distribution, and how it looks like when you increase the number of samples, that it's become better and better to the bell shape. How it looks like t-student distribution when you increase number of samples, and also when you are playing with this degrees of freedom parameter. And also we discussed gamma distribution. Then we talked about measure of central tendency, that you can use mean, median, and mode. And you are free actually to choose which one is suitable for your data. And then also we covered measures of variability, that you can measure variance. You can take a square root and get standard deviation. And when you get a standard deviation, actually you can see how it's affect your data. We actually checked how different values of standard deviation like changes the shape of a normal distribution. Then we discussed about range. This is quite simple. Quantiles, percentiles, and quartiles, which actually is the same concept. This is how to say synonyms, how you can measure them. We discussed 3 sigma rule. 3 sigma rule is useful when you are checking your data for outliers. We discussed about 1/2 interquantile rule. It's also useful for checking for outliers. It is more robust than 3 sigma rule. And then we discussed about rule of big numbers. This concept is important concept from probability theory, and you might be asked about it during interview. It's important to understand how it works. And then we discussed about central limiting theorem, that no matter what type of distribution you have at the first place, after taking the subsamples and measuring mean, you will end up with a normal distribution. Okay, guys, at this point, I will finish today's talk. Thank you for participation, for listening. I'm really glad to see all of you today. I hope to see you next time. And also, please remember about the homework. I will say that deadline for this homework will be in a week and a half. You will submit it. I would say you need to submit it. Let me check. Yeah, I would say on 31st of May. You will have a week and a half because you have almost 20 exercises in it. Okay, guys, thank you. Thank you for participation. I will stop sharing. Okay, guys, see you. Let's stop recording.